Hello all. Today we will discuss about the three-terminal PWM switch model, and we will see how we can plot or extract the power stage transfer function for our buck converter example. So let's start. The three-terminal PWM switch model was developed by Vace Vorperian. He has a famous book also entitled Fast Analytical Techniques for Electrical and Electronic Circuits. Oops, sorry. So we know that all our three basic topologies of switching converters are nonlinear by nature, so we have nonlinear systems. The idea of this three-terminal PWM switch model was to um, create or derive an average model that will linearize the system, and then all known techniques of solving linear systems of equations can be applied. So let's have a closer look on our buck converter. We have here the switching network with the active connection, passive connection, and common connection. Active comes from the switch. Yeah, so we have the active semiconductor. P from passive is from passive semiconductor, and C is the common point between them. So this is actually the switching network, and we have depicted here the topology for the buck converter. So we need to understand what are the how to say, the quantities which are experiencing non-linearities. So if we are looking at the current on the A terminal, well, when the MOSFET is conducting, actually the current on the A terminal is actually equal the current on the C terminal. So it's actually the current to the output inductor. And when the MOSFET is turned off, then we have no current consumption. Therefore, the current in the A terminal must be zero. In a similar manner, we can identify the voltage here on the switching node. When the MOSFET is on, we have the input voltage, and when the MOSFET is off, actually we have the ground potential, so it's zero. So we have these two quantities, which are the current on the A terminal and the voltage on the common, or actually is the VCP voltage, because in this buck configuration the passive terminal is connected to ground. So what we are going to do is to average those quantities over one switching period. So by simply expressing them in this way, 1 second, again I forgot to take my laser pointer. Okay, so now by averaging those two quantities, we can see that, or we can state that actually the current on the A terminal is a function of duty cycle. So it's actually the duty cycle times the average current at C terminal. And in a similar manner, the voltage across the VCP terminals is actually duty cycle times the voltage across AP terminal. Okay, then what we have here is we can create an average large signal model for our switching network in a way that we can express them by a dependent current source, which is actually the first equation, and by a dependent voltage source, which is actually the second equation. Okay, but this large signal nonlinear model needs to be linearized. Therefore, what we are going to do, the standard method, is to introduce a small perturbation, and then we will linearize the model, and we will extract, or we will end up with a PWM switch model in the form that is can be useful for AC analysis. So we are all the variables there. Let's say we are going to uh, we are going to describe them as a DC value plus a small perturbation. So actually the D, which is for the duty cycle, it will be a capital D, which is the steady state value, plus a hat D, small d, which is the perturbation. And we do the same for all the other um, variables, currents through the terminals and voltages. So now if we rewrite the two equations above, we will have something in this form. Yeah. So we replaced with the DC values plus the perturbation. And then what we simply need to do is to do a simple algebra for this to expand the equations, and then we will have a product of two. We will have terms that are products of two perturbations, but we will neglect those terms because we assume the perturbation is small enough compared to the DC level or DC operating point, if you want. And the product of two very small perturbations, then it's a very small term, and that term can be neglected. So after expanding the equations, we can actually extract the terms which are containing only the let's say DC levels, and those are going to be the equations which are valid for the steady state. And then we will have the terms which are containing the small perturbation factor, let's say, on it. So in steady state, we end up with those two equations, and actually those two equations are resembling an ideal transformer equations. That's the reason why in our model we will have this ideal transformer with a turns ratio 1 to duty cycle. Yeah. And then for the AC part, we have two equations that can be translated in a current source, dependent current source, and a dependent voltage source, which are actually those two depicted here. So in the end, we will have a model that is valid also in DC as well as in the small signal. And actually, this is the way how this three-terminal PWM switch model was derived by Varperian. Now, let's reconstruct our buck converter, and it's pretty easy to do this. So we instead of our switching network, we are replacing the model of the PWM switch. So we have the two dependent voltage and current sources, and we have the ideal transformer with this 1 to D duty cycle. And then we have the inductor, the output capacitor, the load, which is depicted here. And of course, so here on this left side, we have the input voltage source. And we can do these identities, or we can identify that actually the VAP voltage is actually the input voltage. The current in the A terminal is actually the average input current, yeah, in our buck converter. And actually the IC, so the current in the C terminal, is actually the output current, because we are doing our analysis for our buck converter in continuous conduction mode, and we know that the average current in a buck converter operating in continuous conduction mode, the average current in the inductor, actually it is the output current. Okay, so what, for instance, in a DC analysis, or what a SPICE program is doing when it's calculating the DC operating point. So actually, um, we have the inductors like a short circuit, and we have the um, capacitors like an open circuit, and of course we will not have any small signal component. And if we do this, we can simply we can apply actually the ideal transformer equation. So we will have input voltage over 1 must equal output voltage over D. So from this expression, we can extract output voltage as being duty cycle times input voltage, which is correct, is what we expect it to be for a buck converter. For an AC analysis, any DC voltage source, it's simply zero, because an ideal voltage source has a zero impedance, so it's just a short circuit. And now one of the most used transfer function we are looking at is the output voltage over duty cycle. Yeah. So what can we see is that actually the output voltage is here. Yeah, and we can simply identify that we have two impedances. One impedance is given by the inductance itself, and the other impedance is just the parallel network of output capacitor and output load resistor. Therefore, it's just like um, a divider, yeah, like a voltage divider with two impedances. So therefore, output voltage would be simply the Z0 of S over the sum of the two impedances, ZL of S plus Z0 of S, times the VCP voltage. Okay, so we actually now we want to write or to determine what is VCP of S over D of S transfer function, because the other part we know it already. So actually, in our PWM switch model, we said, okay, in AC analysis, the input voltage is just a short circuit. That will make that this dependent current source not to appear anymore in our model or in our equations, because actually it's kind of short circuited, if you want. And then we only have the two voltage sources here. So we just need to write the equation, the Kirchhoff, if you want, on this loop. So we have minus VAP over D times D hat of S, which is this voltage source, plus VCP hat of S over D, which is this voltage source, must equal 0. Yeah. And then simply we extract by algebra manipulation, we take VCP hat of S, which is VAP times the hat of S, but we know the identity that VAP is actually the input voltage. So in the end, VCP hat over the hat of S will equal input voltage. Therefore, we stated that we are interested in the V out hat over the hat of S, and we can express this as being a product of two functions, if you want. So is this VCP over D of S, we just saw its input voltage. And the other one, which is V out over VCP of S, we saw that it's just the ratio of the impedances we defined. So here are expressed the two impedances. So now if we put everything together, we end up with actually with this expression. Yeah. So actually we have now this expression of this the most important, I would say, transfer function of the power stage. However, we still have the comparator gain. The comparator, it's this is more related to the voltage mode control, but we will discuss later about this aspect. So in voltage mode control, we have a comparator, and it's the way the duty cycle is actually derived. So we will have at the input of the comparator, we will have um, on one input we will have a voltage ramp, and on the other input we will have the output of the error amplifier. So we know that if we normalize, or if we take the voltage ramp as being 1 volt, for instance, yeah, then this expression is valid. If we have a voltage ramp which is different, then we have to take care of that, and that's the reason why I define this gain of the comparator. Gain for any block, if you want to see it like this, is output over input. Yeah, so output of the comparator would be duty cycle, input would be actually the control voltage, and we know that for 100% duty cycle, yeah, over ramp we will have yeah, 1 over V ramp. So that means we can update the above equation by including this comparator gain, and we can now write the new transfer function as being V out hat of S over VC hat of S, where VC, this is the control voltage. Okay, good. Then we can easily construct this, let's say, AC model, if you want, for extracting the power stage transfer function in a simulation program. So we have the two dependent voltage sources, which are B1 and B2 in this case. And we have the ideal transformer represented by the B3 and B4 current and voltage sources. And then here we have the AC perturbation, and I called this D, which is for the duty cycle. So by simply replacing in our buck model the switching network with those dependent voltage and current sources, we are able to run an AC analysis and get very quickly the transfer function of the power stage. Of course, assuming that we are right now normalized with a ramp. So here it is, the simulation. I can still run it again. So you can see that it's very fast. What I did here, I just stepped the resistance value. So we have the maximum or the nominal output resistance, like output voltage over output current, and then we have twice this value, so half the nominal output current. What I wanted to show with this is that the lower the output current, the higher the peak here. So actually what we have here is an LC filter which has a certain quality factor at its resonant frequency, and the load resistor is actually acting as a damping, so it is worsening the quality factor. So the higher the resistor value, the higher the peak will be. The lower the resistance, the lower the peak here. Okay, let's move back to our, sorry, here. Okay, there is another way how we can actually extract the plant transfer function without being necessary to have the average or the small signal modeling as we did it previously. We can do it directly from the transient simulation by using a special directive available in QSpice. So this is .bode. You can find all the details in the documentation or in the help menu. But here you must be careful about the amplitude of this perturbing signal. So actually what I did, I insert a voltage source here with a 0 DC voltage, but it will have sinusoidal, it will have imposed a sinusoidal voltage with this 15 millivolt amplitude and with a varying frequency from 100 hertz to 100 kilohertz. Yeah. So by doing this, you can extract actually the power stage transfer function very easily. It is very convenient to do this if you have a complicated topology and you don't really know or don't know exactly how to connect or to wire the 3-terminal PWM switch model. This will be this is actually very handy. It takes actually a bit more time, so let me show you. So actually this is the simulation. I run it before, so it takes like 11 seconds to run, and you can see how it looks. This is already half of the switching frequency, and we can start seeing some some non-linearities, let's say, which is probably associated with the switching noise. But in principle, we get about the same result. It's not exactly the same amplitude, and it's not exactly the same frequency we recorded here with the averaged model, but it's very close. And for the quick design of the compensation network is good enough. Okay. Then there is a third way how to generate this transfer function of the power stage. There is a dot measure command in QSpice, and it's this one here. And the method I saw this method presented by Marcos Alonso in one of his YouTube channel videos. So here is the link. You can check his videos. There are a lot of good stuff there. So let's see how it looks. Yeah, it looks like this. However, the simulation time took much longer, because now we are actually doing multiple simulations. Yeah, so we have this frequency parameter, and we step this frequency parameter between 100 hertz and 100 kilohertz with 30 values per decade, right? So we will have like 91 simulations for 3 decades in this case. So it takes a while, and then after the simulations are done, you have to go on the post-process. It takes a while until the results are post-processed, and then you can simply plot the measurements and again take some time to plot it. So this takes a bit more time, but as you'll find on the documentation in QSpice, this seems to be the most reliable way to get the frequency domain response of a power supply. So we have points everywhere. So every point here is just a simulation. Yeah. So in the end, it's more precise. But yeah, in the end, the average model is a very rapid one. We get actually about exactly the same results as for this FRA method, and in the end, it will be your choice how to how to extract the power stage transfer function. Okay, thank you for your attention. That's it for today.